wait. Next Thursday. Okay. Next Thursday, we're gonna have our period quiz. The topic will be A0, A1, and A2. Okay. A0, A1, and A2. That's gonna be covered in our period quiz 1, which is next Thursday on September 24th or 25th. September 25th. Okay? So you can write it down on your calendar about the exam information. Okay? Topic covered A0, air and uncertainty, A1, kinematics, and A2, forces and momentum. Okay? We should be finishing everything in A2 this week. Okay, this week. Alright, now without further ado, let's continue on A2. Okay, so I remember we were somewhere here, right? Did we finish about talking this question though? Yes? Okay, so that's it. Our first, last week, we basically talked about different type of forces, right? We talked about contact force. What is contact force? Well, contact force or forces basically requires objects in direct contact, right? So can you give me some examples of contact forces, Jason? Friction, sure, right? You need to touch it in order to have friction. What else? Reaction, maybe, right? Or supporting force, normal force, Tension, tension. We consider tension as contact force. Then what are some forces that are not contact force? Gravity, gravitational force, electric field force, right, and magnetic force. Okay, and then we learned about calculating the friction, right? We have two types of friction: static friction and dynamic friction, in terms of whether it's moving or not, right? How do we calculate it? First of all, what's the relationship between dynamic friction and static friction? Static friction max. What's their relationship? Dynamic friction is smaller than static friction maximum, right? And for static friction, it can change its size, right, according to the forces applied. It will adjust its size to balance out the amount of forces that you apply until it starts to move. When it starts to move, its nature will switch from static friction to dynamic friction. Now, is dynamic friction going to change? No. Once it starts to move, dynamic friction is a constant. Right? How do we calculate dynamic friction? Did we talk about the formula? Equals coefficient of the dynamic friction times normal force. What about Fs max? Equal to coefficient of the static friction times normal force, right? Or if it's not max, just static force, then it's smaller than or equal to coefficient of the static friction times normal force. We covered those two equations, right? Yes. Okay, good. So let's start from here. Free body diagram we'll also talk about. Did we talk about buoyancy?
No.
Not yet? Okay, well, let me spend a few minutes to quickly go through buoyancy then. So for buoyancy, right, basically it's the amount of force that an object has, let's say, when it's submerged in some certain of medium that's trying to float it, such as in water, right? So when you are submerged underwater, you can feel the upward force that exerted on you, right? So that is buoyancy, FB. So how do we calculate buoyancy? Did I talk about this in MIT? No? Okay. But I believe we talk about water pressure in MIT, right? How do we calculate the liquid of a pressure? The precious liquid. Rho G H, right? Rho G H. Okay. So basically for buoyancy, let me give you the formula first. Buoyancy equals to rho G V, where rho is the density of the liquid, G is gravitational force, gravitational field strength, I'm sorry. V is the volume of the liquid that's being displaced by the object. The volume of the liquid displaced by the object. Okay, that's buoyancy. Did we talk about buoyancy? Okay. All right, I'll give you the formula for now. We will dive into more details later, but now let's just keep. Can I erase it? One more minute. Did we talk about spring force? The force like Hooke's law?
Yes.
Okay. Don't worry. If we didn't talk about it, I'll make sure on Thursday we definitely talk about it. Okay. Now, for now, let's just move on to the second part of A2. All right. Newton's law of motion. So, because we already learned those things in MIP, we're just gonna quickly review it and then mention some important details, and then we can move on. Okay? So Newton's first law is related to certain studies made by Galileo. Okay? And there is a famous stuff of the thought experiment made by the Galileo. If you can see here. So before Galileo, people tend to think that force is the reason that keep things to move, right? Because if you don't apply force to it, the thing will never move. So in order for it to keep moving, you need to constantly apply a force. Well, that seems to be correct in ancient time. Galileo is the first scientist or physicist that stand up and challenge this view of world. And he said it's not the force that maintain the motion. Force is there to change the motion. Object itself has its own tendency to maintain its original motion, and that is the property what we call as inertia. So there is a background story about it. You guys can search it online. So for example here, if I give a car a push on a smooth, level surface, it will eventually stop. But why would it eventually stop? If you don't constantly apply force to it, there's friction between the wheels and the ground. There's air resistance, right? So because we know that. All right, but what can I do to increase the distance it rolls without pushing it harder or changing the slope? What can we do? Oh, first of all, if I minimize the friction, it will go farther, right? So let's say we add more lubrication oil to the wheels. We make the ground as smooth as possible. And we even build like a vacuum out of it to eliminate the factor of air resistance. Now, this certainly will make it go definitely further, right? Because friction is a lot less. Now, add oil. We'll go further. And in fact, he reasoned that if I eliminate friction altogether, the cart will roll forever. Because there's no other forces to stop it, right? No other forces to stop it. So Galileo called that the tendency of an object to not change its state of motion or to maintain its state of motion as inertia. Okay. You just need to take down the keywords inertia. The tendency of maintaining its original state of motion. That's all. So let's move on. Okay. So inertia will only change if there is a force. Well, it's a flawed statement because it's not inertia change, right? Inertia doesn't change, it's the motion. Motion will only change if there is a force, right? For example, it will get slower and slower if there is a friction. Or if you give it a push, it will start to move rather than stay stationary, right? Okay. So that's what Newton's first law coming from. It comes from the basis of the thought experiment of Galileo. So Newton summarized the stuff and then give us the famous Newton first law, which says that velocity of an object will not change if there is no net force acting on it, right? In MIP, what we learned is if the resultant force acting on an object is zero, then the object will tend to do whatever it's already doing, right? If it's moving, it will keep moving in a straight line at a constant speed. If it's at rest, it will keep at rest, right? So similar idea here, right? So in his words, everybody continues to in its state of rest or in the uniform motion in a straight line, unless it is compelled to change that state by forces impressed thereon. Same thing. So velocity equal to zero or velocity equal to constant. Any questions? Very easy, right? Because we already talked about it in 1B. So let's jump. If net force is zero, then velocity is constant. Okay? And actually, this is the condition for translational equilibrium. So now, as we mentioned, the inertia is the matter's tendency to not change its state of motion. So for example, a water balloon is cut very rapidly with a knife. At the moment when the balloon being cut, the water is still have the tendency to maintain its original motion, which is at rest. So what you do is actually like that, right? If you ever watch a slow motion cam, which is kind of popular on Xiaohongshu or maybe YouTube, I don't know. There are a lot of people doing 抽刀断水的视频，有看过吗？然后那种 slow motion 就是你去断这个水的时候，水被切断了，水还 float in the middle of the air, that kind of stuff. So inertia. Or let me do a quick demo here. If I have the Siri, what can I do? I can use maybe a hard card. I will have to sacrifice this. Yes. So let's see. 谁有硬币啊？ Coins. have a coin here. Alright? So this demo is pretty simple. Alright? So right now, oops. Right now, so this coin is rest on top of this cup, right? On this cup. And what happens if I give a hard push of this ruler? The ruler will fly off, right? What about the coin?
It will fall.
Why not move together with the ruler?
Because it don't have inertia of going.
Okay, let's test if it really has inertia. 1, 2, 3. 1, 2, 3. So it falls into the cup, right? Alright, if you didn't see it clearly, I'll do it one more time. 1, 2, 3. Alright, just like还有那种什么来着 Let me give you some demo from YouTube then. I like this one.
3 empty soda cans and a piece of silk cloth. Look at this. Now I will pull the cloth away. 3, 2, 1. It collapses. Ta-da! Surprise! Not me. What I'll do next? I will build my nice tower. And I will now pull this cloth fast. 3, 2, 1. Now it's big. Why? Because these empty soda cans, even if they're light, they still have inertia. When I pull it fast, these soda cans don't have time to
Okay,
move.
so
Yeah.
close it and start from here. Got something like a lock next, right? I don't know. Alright, so let's move on. Examples. We don't do that because it's too easy to that. Okay, second law. Let's quickly recall what we learned about second law. So for second law, first law is talking about when net forces is 0, right? What about second law?
Change of inertia.
There's change. What?
Change of motion.
Change of motion. First law talks about when net force is 0. Second law, of course, talks about the other situation when force is not 0. What would happen, right? When force is not 0, we know that it's going to cause changing velocity, right? For example, I have a plane force. It starts from 0 and then it starts to move, right? So, what exactly does the net force do? It changes its motion, and the bigger the force, the bigger the acceleration, as we already know, F equal to ma, or the sum of the forces equal to mass times acceleration, the product between mass and acceleration. The product between mass and acceleration. Oh, 差点偷了你1块钱. Thank you so much for the demonstration. So far so good? Easy peasy. Because we already learned it. Okay, so again, if A is 0, then resultant force is 0. No problem. 这些都学过啊，不说了。But what most confused all the people is probably the, actually let's do one of the examples here. Let's do this one. Alright. A 25 kg object resting on a frictionless incline is released as shown. What is its acceleration? 3 minutes. You can discuss with your peers. What you're going to do is, whenever you are calculating acceleration, you need to think about the forces, right? So you need to do a free body diagram, forces diagram to this object on the incline. Get used to trigonometry, because in physics we're going to constantly using trigonometry. By the way, for the periodic quiz, there are going to be 50 marks. Okay, so in total 50 marks. And you will have 90 minutes to finish this paper. 20 multiple choices question and 30 points for the structured question. Which means paper 1 have 20 points and paper 2 have 30 points. And for this period quiz, paper 1 and 2 are combined together and will be conducted within the whole 90 minutes. You just need to answer everything on the paper. We're done? Or you guys are confused? Do we need to explain, or anybody can share the answers? 4.95. 4.95. Everybody got the same answer?
Yeah.
4.95? 4.9?
4.9.
Okay. Well, if you're not sure or you're confused, let's look at it together. So, a 25 kg object resting on a frictionless incline is released. What is its acceleration? Now, as we look through the things here, when it's released, right, it's released like that. So since we don't know anything about time, velocity, which means we cannot use savant to solve it, right? The only way to solve it is do a free body diagram. Well, look at this object. Let's pick this moment. What forces are acting on this object?
Gravity.
First of all, weight or gravity. Second of all,
Normal force.
normal force. How do I draw normal force here?
Perpendicular to the slope.
Perpendicular to the contact surface, so N here. Any other forces?
No.
Does it have friction? No. So any other forces? Isn't it should have another force like that? Should it have another force like that? What is this force? Motion force. So let's name it motion force. In reality, does it have this force? No, that's everything. It only have two forces. Gravity and reaction force or normal force. Now, but we know that it's going down, right? So it feels like there gotta be some force that's dragging it downward. But why is it only two force? Well, think about it. So if I have a stuff like this, right? When I put this stapler here, what forces does it have? Gravity and normal force. When I raise the angle, what forces does it have? Still gravity and normal force, but in this case, friction as well. But if it's frictionless, why is it eventually sliding down?
Part of gravity.
It's part of the gravity, right? It's gravity dragging it downwards, but it's part of the gravity. So what you really need to do is, first of all, you identify there are two forces, gravity and the normal force. There's no friction force because it's frictionless, okay? And then what you can do is you can decompose gravity. How do we decompose? We draw a coordinates which is parallel to the slope and perpendicular to the slope, okay? Then this normal force falls onto our y-axis, and then we can decompose this force into its y component and x component. It is this force, Wx, the component of the weight, the gravity on x-axis that drags the object downward. What about component y? What's the function of component y? To balance out the normal force, right? So that the object won't move in y direction. Because in y direction, the normal force is 0. According to Newton's first law, if normal force is 0, then it's either stationary or moving at a constant speed, right? So in y direction, it's stationary. It's not moving this way, right? Okay. So what can we get is we can get that normal force equals to Wy in the y component. And in x component, we only have Wx, right? Now, how do we calculate Wy and Wx? Trigonometry. Okay, so we have a triangle here. This part here is Wx. This part here is Wy. And this is W, right? And this is a right angle. We know that this angle is 30 degrees. So this angle is 30 degrees, right? So Wx is W times, or Wx divided by W. Wx is the, let's say this is the 30-degree angle, which is opposite, right? W is hypotenuse. So Wx over W is opposite over hypotenuse, which gives you sine 30 degrees, right? So you get Wx equal to W times sine 30 degrees, which gives you half of the weight, right? So 0.5 mg, right? 0.5 mg. And since we're looking for acceleration, acceleration is in which direction? Only x direction, right? Does it have acceleration in y direction?
Uh,
Because there's no net force in y direction, so there's no acceleration in y direction, right? So basically, if you decompose the force, this N and this Wy cancel out. The only force left is Wx, right? So Wx is your net force. So you actually got F net equal to Wx equal to ma. Net force equal to mass times acceleration. So which is 0.5 m equal to ma. M and cancel out. So acceleration equal to 0.5 g. If g is 10, then acceleration is 5. If g is 9.8, then acceleration is 4.9.
4.9?
4.9.
No, it's not.
First of all, free body diagram, you only have two forces, gravitational force and normal force. And then we decompose the weight. We get this part, which is the y component of weight, mg cosine theta. This part, which is the opposite of 30 degree, is mg sine 30 degree. So this mg cosine 30 degree is cancelled out with r because there's no motion in y direction. And then in x direction, we have mg sine theta. So this is the normal force. Oh, wait. This is the net force. So net force actually equal to mg sine theta. M cancel out, so A equal to g sine theta. Theta is 30 degree, so you get, well, in this case, it uses 10, so acceleration is 5. We're good? Any questions? Okay, so that's one example question. Just one example question.
用你没有那个 force。
没用啊. You don't need it. That's the thing. In DP level, it's no longer like MIP. It will only give you the useful information. It will give a lot of not related, unuseful information to confuse you, right? So you need to identify which information is useful to you. Okay. Any other questions? So far so good? Okay, let's move on. Now, what about speed? After we figure out that the acceleration is 5. Can we now maybe use Suva to find out the speed now? Okay, 2 minutes to solve it. So Anna? down? Okay. So if we're going to use suva, then step one we're gonna write down SUVAT. What do we know, right? We're looking for speed at the bottom. Is that initial speed or final speed? Final. So we're looking for final speed. What do we know? Resting. So
0 initial.
U is 0. We just calculate acceleration, right? So acceleration we know. Do we know time? We don't know. Do we know S?
Yes, you can.
How can we find out S?
Sorry.
Isn't S the length of this part?
Yes.
And now this information is useful. How do we use it? Well, 30度对应的边是斜边的一半 which is 12 meters, right? Or you use, again, opposite over hypotenuse equal to sine 30 degree, and then you're looking for hypotenuse, which is opposite over sine 30 degree, which is 1 over 2, which is 6 divided by 1 over 2, gives you 12. So S is 12 meters. Then you can apply symbolic equation. Which equation to use? We know S, we know U, we know A, we're finding out V, we don't know T. V squared equal to U squared plus 2AS. So V equal to root of this. U is 0 plus 2 times A is 5 times 12. You get root 120, right? That's the final speed. Root 120, which you're going to get 11. Did you get 11? Good. Any questions? So far so good? Easy peasy, Japanesey. Well, it's just the saying, you know. Okay. Oh, no any disrespectful thing, okay? Okay, we're not going to do this example because it's in the essence about the same. So let's go on to next. We're going to talk about the third law. Anybody still remember third law? What does Newton's third law talk about? It's the law of action and reaction. What's the relationship between action and reaction?
Same magnitude, opposite.
Okay, equal but opposite, that's the core. Let's say, Mindy, can you give me an example of action and reaction?
The ball hits my jump and fall hits my head.
Mm-hmm.
Then
What is action here and what is reaction?
earth and the ball is like half reaction toward the earth.
You have reaction towards the earth.
Then
Why is there a third object of the ball? What does the ball do here in your scenario?
Like the ball hits my head. Then
The ball hits your head,
Yeah.
so
the ball will have like yeah.
the ball hits your head. What is the action force here?
The ball toward the earth.
The ball hits your head and then the ball towards earth has an action? Alright, I'll give you a 5 minutes break to think about your example.
What was it?